Hello everyone, I'm Paolo AI again, your favorite AI nerd. And in this tutorial, which will be probably split in 2 or 3 parts, I'm going to attempt to replicate this Kona model released by Logical Intelligence. It's an EBM model. There is no information how this works. I think if you know where they publish benchmarks or details. And so the idea is, can we build something based on the JEPA architecture that can solve Sudokus of different complexities? On a side note, I already solved this problem using a modified transformer, which you can find in the link below. And that was 3 weeks ago. It was mostly an intellectual challenge, and it worked pretty well. You can see the results, but in this case I just want to use the EBM approach, which I think has a very nice fit for these kind of problems. So where do we start? Well, the first thing is to get hold of a database. Yes, you can generate them, I guess, algorithmically, but I wanted to have something that was like more sort of validated and used by other people. And so if you go on Kaggle, you can find this data set here. So it's a 3 million rows of Sudoku puzzles. And actually they were generated by this generator, and they are sorted by difficulty, which depends on the number of clues given in the puzzle. So if you look at this one, for example, and just picking one, the dots means that there are missing, these are the empty cells, and you have the solution. So it's very simple. Essentially, each row tells you the puzzle, the solution, how many clues are given, and the actual difficulty. And so if you want to explore the data set, I'm not going to do this here because that will take probably more time. But after signing in, you have to put your you have to generate your API key so you can actually download it. So where do we start? Okay. So we want to use JEPA as an EBM to solve a this specific problem. And so what I'm going to do in this notebook is essentially create a pipeline for training JEPA, downloading the dataset, and doing some sanity checks. So these are very important. You want to know if the training is successful. So you need to apply some metrics. Okay, so well, quick theory. If you remember this diagram, so we know that we have essentially, let's say, several components to build a JEPA model, and one is the context, so is X, which in our case is the unsolved Sudoku grid, which is the digits and the blanks. The target is Y, which is the solved Sudoku grid. The mask is essentially Z, which is a binary map of blank cells in the puzzle. And then you have the context encoder, produce the latent representation as X. The target encoder, the Y, produce the latent representations as Y, which is the EMA teacher. And you have the predictor that predict as Y. So predictors takes the state representation after the encoder with the latent and try to predict the S tilde Y. And we know that our training objective is to minimize the norm, which essentially is we are using the MSE error to minimize this the distance between S tilde Y and SY. So essentially, we want to minimize difference between these two, between this and that, right? And this is D. So as you can see, it's pretty straightforward. I mean, what we don't have in this case is A, we don't have an action because in this case, we are not simulating an action on the environment. So we are not changing the environment, which maybe it's something we can do later. I'm not sure if it makes sense to have filling, to have the blank filling as an action. It could be an idea. I didn't want to complicate it unnecessary for this stage, But potentially the action can be simply the fact that you are, filling the blanks. But as it is now, we are using this concept. So I think it is a very natural transposition, and the context and the target, which is the solve. So the first thing I'm going to do is we're going to install some dependencies. I already did that. And the second one is to download the actual dataset, which I did. So you can see the dataset is here. It's quite big, so don't try to open that because it's 511 megabytes. But you know already the structure is here, so you can take a look. Okay, so that's done. I'm going to essentially import all our libraries as usual. I mean, there is nothing really unusual here. And then, well, the first thing you have to do is to build this class. I'm not doing anything complicated here, but essentially the dots that you see in those strings, they become 0, and the solution digit stays between 1 and 9. So the mask Z is 1 wherever the puzzle has a blank. So in terms of masking, so if you look at the Z, you can see that I do the digits replacement here. Okay, of course, I'm going to check if it's like, if they're not 81, if they're 81 is not Sudoku, which never happens. And you get this 9x9 grid. And essentially you have like X, Y, Z. And as I mentioned before, you're basically checking if it's empty or not. Okay. So yeah, so if it's empty, it's going to give you essentially a 1. So yeah, this is nothing really fancy. I do then some sanity checks. So sanity checks, what's happening here? Yes, we know it's a CSV file, but I just want to make sure that the shapes, the value ranges, and masks are all correct. And like, in case there is some errors. But okay, that looks it looks fine. So X goes between 0 and 9 because we have blanks, and Y, which is the solution, needs to go between 1 and 9. So the solution needs to have all the solutions, and the shapes looks fine. And the mask density is around 60%, which, I mean, this is an average. Of course, some of the puzzles have less, some of the puzzles have more. Okay, so the first thing we do, of course, is the usual train validation split. So what I'm using here is 95% to 5%, and the data loaders use batch size of 128 on GPU with this memory, so that, I mean, we are using the default Colab. It should be faster for transfer. And then the split uses fixed generator seed, so you should be able to reproduce it. Okay. So yeah, in this case we have 743 train batches and 40 validation batches. Okay, so next I'm going to just visualize one of the puzzles. So this is quite simple, just to make sure that this representation works. And yeah, you get this puzzle. I'm not sure what's the complexity for this one. It's probably a medium, and the actual solution. So X is the puzzle and Y is your target. So X is the context and Y is your target. Okay, so everything it's fine. And now, well, we have to build the baseline architecture, which is the fun part, okay? And I'm not Andrei Karpati that can type all of this, so I sort of copy and pasted this. But you have 3 main components. So you have the Sudoku encoder, which is essentially doing the embedding. And this one is 2 convolutional layers with batch norm. And ReLU. So I'm not using the CLUs in this case. There is another tutorial where I explain the difference between ReLUs and CLUs. but it doesn't make a big difference. Then we have the transformer predictor here. So transformer predictor, you flatten the 9x9 into 81 tokens, add a mask embedding, and one-dimensional positional encoding. And essentially, it's a free transform layers. Now you will say, well, why using transformer? Like, is it cheating? Well, the difference is that we are not using the transformer to generate the solution. It's just the predictor component. Okay, so we're not using a generative approach here. It's just that the transformer it's very well suited for this specific because in Sudoku, as I mentioned before in other tutorial, you need to have the attention that relates to the grid, the row, and the column, and the overall puzzle. It's better suited to be the predictor. Okay, and then I have another class which is the Sudoku JEPA here. And the Sudoku JEPA wires all these components together. So you have the exponential moving average update, which is the let me see, what is it? The P target. Here, when you do this update, you can see that essentially I'm combining the predictor target plus the predictor context with the moving average. Okay, so as you can see, you have the context encoder, the target encoder, and the predictor. Now, you can, if you want, change this transformer predictor to a CNN. I already tried that, and I can tell you it wasn't working very well because, the attention is missing, which is kind of important. So, but you can still try to replace it with a CNN, and you can play with that. I mean, it can be anything, right? It doesn't have to be a transformer. Okay, so what do we do here? Very important, the training loss. So the training loss is the MSC in latent space. There is no reconstruction term. There is no contrastive negative. The only signal is essentially your predicting embedding should look like the teacher's embedding of the solution. Okay, so it's exactly as in my previous tutorial. You're just using the mean square error. Okay. Okay, so well, let's go for the first run. So we are going to train a this is roughly 1.199 million parameters. I'm not sure how big Kona was, so I kind of sort of dimension it this way, because in my previous experiment I work with a slightly larger model. I think 1.19 is good enough size, but of course, we can also try to change that later. And so when we run this, I'm choosing, as you can see here, hidden dimension is 128. We have a learning rate of essentially 10 at -4. Weight decay is also 10 -4, and we are using the good old Adam optimizer. So very, very simple, nothing super fancy here. We can then have, you can see here, we have the main training loop for each epoch. So once again, there is nothing particularly different from what we have seen before. So after each epoch, the only difference here, okay, so let me call you through this. We have the usual gradient for the trainable part. We have the clip gradient normalization, which I used before, and essentially we log those losses. I want to make sure that we are logging those. But another things I added was the estimation for the embedding variance. So this is important because we want to make sure, as you remember, that this thing is not collapsing. Like you might have a great loss function that goes down, but actually the model is collapsing, which is a very common problem with JEPA. And so I set something like 10 and minus 4 as a kind of a quick check to see if this is collapsing, okay? So if you run this, yes, I keep track of the history for each epochs. And so we measure the train loss, validation loss, and the variance stats. Okay, so we plot all of this, and la, we can see that within these 10 epochs, you have the train loss, the validation loss, the context, the variance of the context, the variance of the target, and the prediction variance. So yeah, there are some issues here, as you can see, right? And the issues here is that this variance is a little bit too small, which means probably that we are collapsing the representation. I mean, not we, but the actual model is collapsing this representation. And so, well, this is a problem. As we mentioned before, we need to find a way to push the teacher and the student to kind of challenge themselves so they don't essentially copy each other, right? So they have to work harder. And so what I did next, I call it the stability package. It's like European Union packages, but the idea is that because we have this kind of low embedding variance, we are going to try different things. So we are going to add a VCRAG on the compute loss. And this VCRAG was actually described in one of papers from JEPA. And essentially what happens is a style variance hinge. If the per dimension standard deviation of the embedding drops below 1.0, there is essentially a penalty, which should find collapse. I also then changed the larger embedding for initialization. So instead of doing the normal ones with standard deviation 0.1, the default uniform initialization was getting 0 values. That batch norm was amplifying to a constant. So the idea is essentially change the defaults, right? And number 3, I'm using layer norm instead of batch norm. So layer norm essentially has no running statistics that could lock into a constant output. And then there's also the predictor bottleneck. So if you project down to 64 dimensions before the transformer, this should prevent the predictor from just copying the input token by token, which is another collapse mode. Okay, so if we do all of this, you can see here. So all the functions are defined. So it's just defining them, and we are going to essentially rerun this. Okay, and then we are going to compare all this methodology with this with the previous one. Okay, so this is going to take some time. I might pause and come back. Let me see. Okay, we are doing some progress. So I'm plotting once again the train, the essentially loss. So the train total loss, the MSEs, the train variance, the validation total, and the MSEs, essentially all the metrics that we need, including the context and the target. Okay, I'm going to come back in a while because this is obviously taking some time. Okay, it's still running. So we are on epoch 8, so we'll stop at 10. And just to check quickly, you can see that the total train loss is going down. Great news. The mean square error, it's kind of like I mean, it's going to be up and down, so it'll be unstable. And the validation total is going down, which is good news. So we're not overfitting. And then I also calculate the MSE for the validation. But the most important thing is that this time we have the variances, which, I mean, they're still small, but not too small. Okay, so now let's plot them, because I mean, looking at these numbers, it's really hard. Okay. Okay, so how do we interpret this? We had the loss curves on the left by epochs. So we have 10 epochs, so there should be, well, it's 9, so starting from 0. And on the other side, we have the variance comparison, right? Which tells us if it's collapsing or not. So if we see the original run, so let's say the naive run was the blue and the orange, they were really promising because the loss was already smaller and it was going down towards 0.2. But with this new modification, we have a slightly higher loss, of course. Yeah, so there is no free lunch. And so the what I call the stable version start from the training validation start from slightly higher loss, but they seem to go down and stabilize. Now, the most important thing is this variance comparison. So I set this arbitrary threshold of 10⁻⁴. Just as an indication whether there is collapse or not. And you can see in different colors that the baselines before was the blue one, where this was going down really to a very small number. So this means that, yeah, the model was definitely collapsing its representation. And the orange part, yeah, this was for the predictor, was also going down. But well, sorry, the baseline is the blue one, which was the blue was going down. Now with the new version, I plotted the predictor, the context, and the target variables, and as you can see, the variance seems to be pretty stable. So it's not going down, it's going a little bit up and down, but that means that we have probably achieved a very good representation. So what do we do after this? We do have we do still have some problem, right? So the stable run stopped collapsing, but the variance is still kind of, I want to see if I can do better, essentially, right? I don't want to have these variants. I want to see if I can pump it up a little bit, right? So, well, what can we do? And to be honest, I had to play with this a little bit using different techniques. But I made like five changes. So the first one was increase higher variance target in the VicRec style. The second one was to increase just the variance weight. I also added a covariance of diagonal penalty, which I called the compute loss volume. So this penalizes the correlated dimensions. So the idea is to force the 128 embedding dimensions to encode independent information rather than redundant copies. I also added a deeper transformer predictor. So now it's 6 layers, 8 heads, and two and so essentially, 6 layers, 8 heads, and instead of a flat one-dimensional sequence position, we have a 2D row and column positional embedding to kind of understand the constraints of Sudoku, right? And so the row and the column embeddings are summed at each of the 81 cells, which lets the model kind of understand that the row and columns and structure, rather than considering the grid as a sequence. So this is the things I was mentioned before. It's kind of giving it the opportunity to understand this constraint. Then I did some dynamic masking, which essentially hides more information. So during training, I did another 20% of cells as randomly hidden. And so the idea is to kind of force him to generalize a little bit more rather than memorizing. And then I did another trick with the EMA cooldown, which, I mean, I've seen this in traditional deep learning where you start from a higher and then you decrease. But yeah, it's starting now at 0.99 for the first 3 epochs. And so the teacher moved fast. But then ramp ups to 996. So actually it's increasing, not decreasing. Like in the learning rates, this does the opposite. You start from 0.99 at the beginning, and then you sort of go up a little bit. And so, well, I mean, the idea is like, okay, you know, we'll still want to see if the predictor variance, you know, we don't want that to go like, let's say, towards 0. And, you know, it needs to sort of go above if we can. And both the context variance and the target variance, which were the green and the red one, the green and the red one, needs to essentially like go better, right? So yeah, you can see the implementation here. So we have the new transformer, which again, I mean, is nothing really sophisticated, but you can see that you have the row embeddings and the call embedder with the, you know, the mask projection as well. And so let's run these again. Okay, and this is probably going to take some other time. I'm going to pause and come back. Okay, training is starting with the first epoch for the what we call the volume version. I'm also monitoring the GPU RAM to kind of see if I'm using too much memory, but it's only 1 gigabyte, which is great. So it's not like doing a lot of work. So I was thinking this would just die, but it seems to be going well. And well, something I want to say is that when we run this volume, and I call it volume version because I'm doing this compute loss volume to avoid to penalize this correlative dimension. When we do this, as it's coming out, we want to see the same thing. So first of all, the EMA value should, yeah, so you can see starting at 0.99, and you should go up essentially over time. The dynamic masking is only applied during training, so the validation sees the clean, unmodified puzzle. So when I calculate the validation error, obviously it's not done on the additional masked version, right? It's just done on the original one. And of course, I'm saving the checkpoints because like I don't want to run this again. And the checkpoints are saved here. So this was the original one, the first run, let's say. This is the stable version, which we did before, and now there should be this volume version of the checkpoint that is running now. So let's check quickly. Train total is going down. Mean squared error is going down. This is the variance. Okay. This is the other measures. And yes, if you want to see, well, obviously it's in the code, but I just want to make sure that this variance doesn't go down. Okay, so the context variance 7, so 10 minus 4. Okay, is decreasing a little bit. Target variance is between 3, 4, and 5. And prediction variance, the variance of the predictor is around 4, 2, and 2. Okay, let's keep monitoring. All right, I'm back. How many minutes? Let's see. 11 minutes. That's not too bad. So we did 10 10 epochs. As you can see, the EMA have increased over time, and now we have to look at the variances to make sure that hopefully we have improved the actual results. And that's saved as underscore volume here, so your checkpoint is that one. And so now let's do a quick comparison again. So hopefully is what we're expecting. So we have so 3 main charts, okay. Where do we start? So on the left we have the validation loss. So what you can see, the volumes, which is the last run with all this changing, has a higher MSE than the stable run, which was the second one we run. So let's say the naive one was the baseline blue, the lowest one, and then we have the stable one and the last one. So this actually increased. But I think is a good sign. I mean, it is higher, but if you look at the variance on a log scale, the CTX, the context variance, and the target variance are climbing above the 10 at -4. So if you look at the volume, here we go, these kind of volume ones. Yeah, so the purple, red, and green, are sort of the higher one compared to the other one. So remember the baseline went down, like just crashing down, and then the stable one was the orange one for the predictor was here, but the new ones, which is the volume versions, are very healthy and sort of like going up. So this is a good sign. And on this right chart, we see the volume internals. So we have the variance hinge loss. This is just for the volume version. So we know the EMA. Well, this is just, you don't really see the big difference, but let's say it's around 1. But then the volume, the variance hinge loss, and the covariance, for covariance loss. And the so the covariance term should decrease as the features become decorrelated. So that looks good. So well, now this is the kind of fun part. How do we know that he has learned something useful, right? So what you can do is so we take the last checkpoint. That looks good. And then the idea is we can project the embeddings into 2 dimensions, okay? And you have 2 ways to do that: the good old PCA, principal component analysis, and the TSNE to inspect the latent structure. So what we really look for is the gradient by blank density, so the points colored by the fraction of blank cells. So if you have a smooth color gradient, so dark to light or vice versa, from one of the scatter to the other, means that the model has learned that harder puzzles have more blanks, and that should have a different region of the latent space. Then you can also look at the context versus the target alignment. So the context embedding SX come from the incomplete puzzles, but the target embeddings come from the complete solution. So if the 2 plots have a similar global shape, like the JEPA alignment is working, and so the predictor learned to bridge the 2 views. Spread, not collapse. So after this volume run, push the variance up, you should see that the points spread out on a 2-dimensional space rather than clustering into like a ball, right? So a collapse model means you have a dot. A healthy model should be something like a cloud or a structural cloud or something. And for TSNE clusters, they should, you should have clusters or arcs. Maybe they should correspond to different bands or structural families. So I was running this before. Okay, so we know the embeddings. So these are the embeddings. We know the kind of blank density range. we know the context standard deviations for the context and target, which, yeah, it's not too bad. Okay, let's look at the PCA. Okay, so we have two components. I just choose the two components. So the context embedding is on the left and the target embedding is on the right. They are both colored by like blank density. So blank means how many things are essentially missing. So the explained variance ratio, a high first component means the space is still to one-dimensional. And whether the color gradient is smooth or random, right? So smooth gradients means difficulty is sort of encoded in the first principal component. So yeah, there is, I'm not sure if, I mean, I can see some sort of, if you look at the blank density, there is some of them are here, but I also some points on this side. So the good thing is not like I mean, I see some separation here with the kind of yellow ones around this area. The greens one are here, and the difficult ones are sort of on the side. So I'm not sure, like, if, I mean, could it be better? I don't know. And well, the target embeddings, it's kind of like slightly better. I mean, there's more like of a shape here, but yeah, these blank density, some of them are here. I mean, it's a little bit more mixed. So I'm not sure. I mean, I thought it was a good idea to plot it, but I can't really tell, how this should look like. Let's see Disney, which is what people usually do. So this should be the non-linear view. So PCA, remember, is always like always assume a linear representation. Disney gives like a non-linear two-dimensional view. So let's see if there is any, I don't know, any sort of topological structures here. Like maybe we see a uniform cloud, which is also, I mean, is not too bad. And yeah, so I kind of, this takes more time, okay. So yeah, so yeah, so it's still two dimensions, so we can actually visualize it. We still plot the blank density. And so this is still the context embedding, and like, I don't know. I mean, there are definitely some colors on this side, some sort of gradient here moving left to right, but I can't really tell if this is good. I mean, I was expecting it to be more, maybe, differentiation. And yeah, so, if you, I mean, essentially what I was expecting, some sort of a smooth color gradient by blank count, but I don't really see this. I mean, I see a little bit of that, but not so much. And then I also plotted the the volume run, so the MSE, the variation hinge, and the covariance regularization, just to kind of see, okay, by epochs. So we have the train MSEs is kind of like increasing a little bit, and then we have the kind of volume. I mean, the volume version, the train total and the validation total going down. So there is some form of learning happening. And in terms of the variance curves, these looks good because they're not collapsing to zero. So yeah, I don't know. I mean, it looks decent. And what I was to say, yeah, I put some notes here, like how they should look like. And maybe I will do another tutorial after to kind of play with this. But I think this is a good first attempt for having like a word representation for Sudoku. And yes, no, feel free to play with some settings. Maybe you can get a better separation here. But what I will do in the other tutorial, so first of all, what we can do is we can try another type of predictor. So I was thinking maybe a CNN, because I went straight for a transformer, but I want to look for just a convolution neural network, maybe as a predictor or maybe as a graph predictor. So because Sudokus can be represented as graph, where each cell or a node have edges to its row, column, and box pairs. So maybe we'll give you a better constraint-aware predictor. So yeah, I went for the transformer because I kind of used it before, and it was giving me some interesting result. And I mean, I'm not sure how to, like, if this is good, but what we're going to do in the next tutorial, I'm going to actually try to apply inference and take a few Sudokus from the validation set, and just to see what's the kind of prediction. So how does he feel them, right? Because yeah, I mean, like this is kind of new to me. Like, how will this look like in a healthy JEPA? I'm not quite sure, to be honest. So this was purely on intuition and try to get this one going down. And I was probably going to try all of them in the next inference phase, because yeah, the total loss is a little bit higher, but it's kind of stable. And so, well, feel free to play with this notebook, and I'm going to see you in the part 2 where I'm actually going to do some inference. Thank you, and see you soon.